study what are elementary row or column operations or transformations, and using this, how can we find the inverse of a squared matrix? That is the topic. And it is very important. You get a 4-mark question or maybe sometimes 6-mark questions of finding the inverse of a matrix using elementary operations, row transformation or column transformation. So let us first of all see what do you mean by elementary row or column operations. Elementary row operations, row or column. Operation. Sometimes instead operation we also call it transformation. That is elementary row operation or elementary row transformation, or maybe elementary column operation or transformation. So let me call it elementary row transformation. There are 3 elementary row transformation and similarly column. There are 3 elementary row transformations. Number 1, and using these 3, we can then work out the inverse of a squared matrix. Interchange of any 2 rows. First is interchange of any 2 rows. Or if we are working with columns, then columns or columns. That is, any row Ri may be interchanged with Rj. This is column, this is the symbol, or maybe any column Ci be interchanged with Cj, whatever is required. Now, for example, given is a matrix A defined as 1, -2, 3, 4, 0, -1, 5, -3, 1. Then, if I give the instruction R1 interchange with R2, so then it will become, we can interchange. So the second row will come to the first row, that is, we'll get the new matrix as 4, 0, -1, 1, -2, 3, and the third row will remain the same, that is 5, -3, 1. So we get, after applying the first operation, 4, 0, -1, 1, -2, 3, 5, -3, 1. That is the first operation that we can interchange any 2 rows or column. The second is multiplication of the elements of any row or column by a non-zero number. Multiplication of the elements of any one row or column by a non-zero number. What do you mean by this? For example, given is a matrix A, let's take an example. Given is a matrix A equal to same 1, -2, 3, 4, 0, -1, 5, -3, 5, -3, 1, and you want to apply the operation R3 to 5 times R3. What do you mean by this instruction? That replace R3 by 5 times R3. The new matrix so obtained by this elementary row transformation will be the first 2 rows, 1, -2, 3, and 4, 0, -1 will remain the same. To the third row you multiply by 5, you get 25, -15, and 5. That's what you mean by the second operation, that multiply the elements of any row or column by a non-zero number. Now the third operation is addition of the elements of any one row or maybe column to the corresponding elements of any other row or column multiplied by a non-zero number. For example, again, let take an example. Let A equal to 1, negative 2, 3, 4, 0, negative 1, and 5, negative 3, 1. Then, what do you mean by this instruction? That R1 to, what do you mean by instruction? R1 changes to R1 plus 3R2. After this instruction, the matrix will change to, means you multiply R2, the elements of R2 by 3 and add to the corresponding elements of 1. That is 4, 3, 12 plus 1 makes it 13, and 0 of course multiplied by 3 doesn't matter, so it will remain negative 2, and negative 1 multiplied by 3 makes it negative 3, added to 3 makes it 0. And of course rest two rows remain the same, 4, 0, negative 1, and 5, negative 3, 1 will remain the same. So here I discussed three, I repeat, operations, elementary operations or elementary transformation. One, we can interchange any two rows or column. Second, we can multiply the elements of any one row or column by a non-zero number. Third, we can add to the elements of any one row or column to the corresponding elements of any other row or column by after multiplying by a non-zero number. So these are the elementary row transformations. Now next, what do you mean by invertible matrices? Invertible matrix. What do you mean by invertible matrix? Given is a squared, remember, squared matrix A of order M, or you may write M by M. Given is a squared matrix of order M, and if there exists another square matrix B of the same order, that is of order M, or you may say M by M, such that the product AB is same as BA is equal to the identity matrix of the same order. Then B is the inverse of matrix A, B is the inverse of matrix A and is denoted by A inverse. That is, if AB equal to BA equal to I repeat, then we say A inverse is B. Now let's take an example. For example, if we are given a matrix A as 2, 3, 1, 2, another matrix B such that 2, negative 3, negative 1, 2, then let us find out the product AB, that is 2, 3, 1, 2 multiplied by 2, negative 3, negative 1, 2. You know the definition of multiplication, row to column, and the multiplication is possible because both the matrices are of the order 2 by 2. When you multiply, you get 2 into 2, 4, minus 3 into minus 1, so 4 minus 3, and then you get, 2 into minus 3, minus 6, and 6 into, and 3 into 2, 6. And likewise in the second column, second row, you get 2 minus 2, and minus 3 plus 4. So you get 1, 0, 0, 1. So here we find that AB equal to the identity matrix, and of course similarly we can prove that even BA will be equal to I. BA is also equal to I. So under this condition we can say that for the given matrix A inverse is B. So whenever we can find out, given is a matrix A, and if we can work out a matrix B such that AB equal to BA equal to I, then A inverse is B. Now concerning inverse of matrices, we have two theorems. Theorem 1, please note down the statement, inverse of a squared matrix, if it exists, is unique. Inverse of a squared matrix, if it exists, is unique. Now take the proof. Given is a squared matrix A of order M. Now if possible, B and C are two inverses of A. Let B is inverse of A as well as C is inverse of A. So if matrix B is inverse of matrix A, then AB equal to BA equal to I. Call it 1. And similarly, if C is also inverse of A, then AC equal to CA equal to also I. Call it second. And now consider B. B may be written as B into identity matrix I, and this I may be replaced by AC, because C is the inverse of A, so AC is I. By associative property, the product may be written as BA times C, and BA is already, we discussed, is identity matrix. I into C is C. So what do you find finally? That B equal to C. So there cannot be two different inverses of a given squared matrix. It will be unique. Now let's take a second theorem, theorem 2. Theorem 2. Theorem 2 is that if A and B are two matrices, then A, B inverse, and both of them are invertible. The inverse of A exists as well as inverse of B exists. Then the inverse of the product, that is AB inverse, will be the product of their inverses but in reverse order. That is AB inverse equal to B inverse into A inverse. Let us prove it. So consider AB into AB inverse. You know, the product of a matrix with its inverse, that's why it is inverse, is the identity matrix. Now multiplying both sides by A inverse, you get A inverse into AB into AB inverse equal to A inverse into I. Now by rearranging the brackets, you get A inverse into A into B into AB inverse equal to A inverse into I will be A inverse. And now on the left, A inverse into A is identity matrix. So IB into AB inverse equal to A inverse. Now I into B is merely B, because multiplying by identity matrix to a given matrix doesn't matter. So B into AB inverse equal to A inverse. Now multiplying both sides by B inverse on the left. So you get B inverse into B multiplied by AB inverse equal to B inverse into A inverse. And you know B into B inverse will be again identity matrix. So identity matrix times AB inverse equal to B inverse into A inverse. And identity matrix multiplied by any matrix doesn't matter. So finally we get the required result that AB inverse is B inverse into A inverse. So here I defined you the elementary row transformations, and you know what is the inverse of a matrix and few theorems. In the next class we will study how to find the inverse of a matrix using elementary row transformation.